we're able to generate theorems about what these polymorphic or generic functions do, what the function does. So we have kind of free theorems, as the paper called it, but we still don't know what the function actually does. So then we are reduced to writing some kind of unit test, but not the standard kind of unit test that you're thinking of. There's other ways of writing tests that kind of really actually tell us what is going on. So I'm going to talk about property-based testing, and I'll call these writing tests that actually find bugs. Jessica Kerr on Twitter is kind of really into property-based testing. I don't know if anyone here knows her, but she does a writing test first forces you to think about the problem you're solving, but writing property-based tests first forces you to think way harder, which is accurate, but I will claim that that's not a bad thing. So what is property-based testing? Property-based testing is when you make statements about your code in the form of, for all input x, some statement y is true. And then you verify these statements over many different automatically randomized inputs. So you're not coming up with the input to test your function, it's doing it automatically. So it automatically covers a lot of the edge cases that we forget. It's covering bounds that might overflow. It's generating this test input automatically. So this is Haskell syntax. I'm going to go over it. It should be fairly easy to understand, but I will explain. Don't worry about the first line, just worry about the second line here. It says, I have a function called proposition reverse. It takes some list of a's called x's, and it says if I reverse the list twice, reverse it once and then reverse that output, then I get the original list back. So if I have some list of a, it can be any type a, doesn't matter what, and I reverse the list twice, then I get the original list back. And if I run the test suite over that function, I can see that it did 100 randomized inputs, or 100 randomized lists, and it was true every time. And we can see, here's another example where if I have three numbers that I want to multiply together, three integers, and I want to check if the function obeys the associativity laws, again, I can do the same thing. So I have three numbers here, integers, x, y, and z, and I can group on the left, multiply, and then multiply by z, or I can group on the right and multiply by x. And I run the test suite, it passes again. But what about a counterexample for this? Floating point arithmetic. According to the IEEE standard, floating point arithmetic, multiplication of floating point arithmetic, is not associative. So if we change these integers to floats and do the same thing here, we should expect it to fail, which we can see that it does. And it says the tests were falsified after 9 tests. And here's the exact input that fed the function and failed. So we can say that it's generating the input for it. We're not coming up with the test input. It's testing it for her. It's checking edge cases. It's checking all these things that we forget normally. It's generating for us. So property-based testing exists not just in Haskell. It started as an academic project in Haskell, but it's been ported to many, many, many different languages. There's a few in Python. That's kind of popular in the Fedora community. It's Yum and all the Fedora infrastructure tools are Python and whatnot. So there's a whole list of them in Python. There's ports to Ruby, ports to Java, Scala. Pretty much every language that you might want to use, there's probably a port of this property-based testing system. It's usually called QuickCheck. And you can find it and take advantage of it. It's very useful. So just kind of as an example of using it in Python, I ported some of the examples that I just showed to Python, and see that it takes an integer. It's taking a list of integers from 0 to 1024, And it's reversing it twice here and making sure that it matches the original list X's up here. And we can see that it passes. And similarly with integer multiplication, same thing. Passes 100 tests. You can change the number of tests that it runs, the number of inputs that it generates. So if 100 is not enough and you think it's still missing edge cases, you can tell it I want to run 1,000 or 10,000 or whatever. It'll take longer to do that, obviously, but it'll give you more sense of this code is doing what it should. And here's again the example of the test failing. If you use floating point arithmetic instead of integers, and it does the same thing as what the Haskell version did. So it'll tell you here's how many tests passed and failed, and here's one of the sets of data that it passed the function that caused it to fail. So then you can go back to the code and say, I know this input is not working. Why is it not working? And you can debug. So next I'm going to go talk about a kind of a crazy but really awesome academic active research topic called dependent types. And there's a whole lot of research going on in this area, but I think it's worth at least bringing some attention to. And so I'd like to just discuss it briefly with an example, I think. So a dependent type is a type that depends on a value. And dependently typed languages, 3 examples of them are add, hop, and interest. And these 3 are packaged already in Fedora. So if you, if this sparks any interest and you want to play with them, you can go download them and install them in Fedora. They're already there. So here's kind of a boring canonical example. And this is using Idris syntax, but I'm going to explain what's going on. So this function says, here's the inputs to the function. If I have a vector, which is like a list that has a length specified, I'll show you what I mean. If I have a vector of A's, any type A, that is of length n, and I have a vector of A's that is of length m, the return vector that I get should have size n plus m and still be of type A if I append them together. And so that is the type of this function. And anything that does not implement, any implementation of this function that doesn't match that type, if it drops elements from the resulting vector, for example, somehow, it won't type check, it won't compile, and you will not get a binary. So a couple things to note is the function terminates, it's total. We have the total keyword here. In Idris, that means turn on the totality check and make sure that the function doesn't do anything weird like go into an infinite loop or throw an exception or something something that evades the type system. So the function is total. It will always return. The function must have a length. The vector that the function returns must have the length, the sum of the lengths of the 2 inputs. So n plus m elements. And otherwise, it simply would not have compiled. So here's kind of another motivating example. I'm going to kind of go through this a little bit quickly, but it might spark some interest. I have a friend, his name is Brian McKenna, who is into programming language theory research as well, and he contributes to Idris and enjoys working on this stuff. And he made a YouTube video of implementing dependent types, a dependently typed printf function. And the idea here is that when you look at the type of the printf function that he implemented, it takes a string, which is the format string. So is anyone not familiar with what normal printf looks like in Java or C or? Okay. So it takes a format string, and the rest of the type of the function depends on the format string that you're getting, the S here. You can see that later in the type signature of the function, we reference that S, and this is actually generating the rest of the type of the function. And so the practical benefit of this is that if I call printf, with this format string that says a string and a digit, but I pass it two strings, that's a type error. So it will not compile. Whereas in other languages, there's no way at compile time to check that you're sending printf the right things. This will just not compile. It'll say your code is wrong, go fix it and try again. Similarly, if I pass too many arguments to a printf call, I'll get another kind of type error, and it'll say that what you're doing makes no sense. It just won't compile. So unit tests, by one of the things we said unit tests, I said unit tests. Often we look for unit tests to do is find bugs early. Well, how earlier can you get than just not producing binary if it's wrong, right? Like, that's the earliest you could possibly prevent bugs. And here's another example of not passing enough arguments to printf. And you see here the result is something that takes an integer and returns a string. So if I printf here, it takes the format string says it takes a string and a digit. I only pass it a string. Then basically this type is saying, oh, well, you still need to pass an integer before this eventually gives you a string that is the format string here. So it won't type check because you haven't given enough arguments to the function. And here's a non-counter example where it's actually doing what it's supposed to. So if I pass it, here's the format string, pass it a string, I pass it a number, and it does what you expect. And so briefly, I'm going to talk about code review. I talked about this last year at the last block. I don't know if anyone came to that talk, but I don't have a whole lot to say about code review. I think kind of most people here know the general idea of code review. But it's useful for fleshing out ideas and for kind of talking over implementation details with coworkers, with other community members. It's easy to be thrown a software problem and immediately come to this idea of how it should be done. But if someone doesn't look at it and say, hey, you can do it differently, you can do it more efficiently, or there might be a better way of doing this, then you will never come to know that potentially. Code review is basically a chance for that to happen. It's a chance for you to come to know that there's better ways of doing things. By working with the community. It's also useful for pointing out ways of abstraction. So if we write functions that are, for example, if we write functions that should probably work over multiple types, where we limit them to one type, code review is a chance to talk to somebody and say, hey, you can probably generalize this, and maybe it's useful in more ways than the way that you thought of it first. So there's a couple tools out there for doing code review. One that I like a lot that is used in the Haskell GHC community is called Fabricator. And you can see somebody sent a patch here to GHC, and one of the contributors said you can use this instead. And instead of this whole mess up here, you can use this, and it will do what you want. It's a lot cleaner, a lot nicer. But you can also just use GitHub, and GitHub has inline comments where you can comment on a commit or a specific line of a file, and kind of point out that there's different ways of doing things. Just like normal code review, except using GitHub comments. We use this a lot in the Thor infrastructure for our applications. Kind of have an unspoken rule that before code goes into one of our applications, it should pass code review. So basically, we send a pull request to our own repository, and somebody else on the team will review it and say, that looks good, or you can do things a little bit differently. So, kind of in summary, I think I'm kind of on time. It might end a little bit early. Kind of in summary, tests of any kind are useful if they're actually run. So, even if we say that unit tests are the answer, it helps to at least run them, right? And we saw in the beginning that we're not doing that in a lot of our packages that have a lot of bugs reported on them. I would claim that types are awesome if you're given an expressive enough type system to actually do things with it and prove useful things with it. When possible, try to make your bugs prevent compilation. So instead of relying on somebody having to run tests as a separate part of the build process, try to make the bugs just not make the code compile, because we want to find bugs early. And again, what earlier way of finding bugs than just preventing a binary from building if it's wrong? If it's not going to work, why produce a binary? Make it work, and then once you know it works, produce the binary. Property-based testing finds way more bugs than unit testing because we don't have to come up with the input ourselves. We can rely on the computer. The computer is good at coming up with random inputs for us. It's good at coming up with edge cases to test. So let it do that for us. And tests of some kind, property testing preferably, but tests of some kind are necessary to the extent that you don't have a type system that lets you prove useful things about your code. So don't rely on tests to reason about code. When you can, rely on types, because again, it prevents compilation. The code won't compile if it's wrong. And try to use languages that make this possible to do. So let's not insist on writing buggy code. We can do better. We've done better for many years in academia. The tools mentioned in this talk are just kind of one step forward in this. It takes a lot of effort. It takes working with people, showing them these tools. That's kind of why I submitted this talk here, because I wanted to kind of spread awareness of these tools a little bit and show that there are other ways, not just unit testing. There are other ways of kind of getting us closer to correct software. And again, we can do better. We already have. If you look at programming language theory research in academia, this stuff has existed for a very long time, but a lot of people don't really know about it. So the industry just needs to catch up. So that's my contact information. If you want to reach out, if you have any questions on any of this, feel free to reach out to me on there. It's my email address, Twitter, IRC, and that is my presentation. If anyone has any questions, I think we have a few minutes.
Maybe can the summary related to unit testing and prototype testing be said like in the unit testing you are testing or providing concrete values, while in the prototype testing you are formulating rules how to test, the rules the test need to pass.
Yeah, so you're writing universal rules. Like you're saying this function has to work for every possible input of this type, rather than just this one specific case. Anyone else?
The